Okay, so let me first quickly do a recall about the file system, because actually last time I think there are some concepts I did not really describe that well, so I'll give you some examples later. So first of all is file, and the file is a linear array of bytes. I think it is quite simple. So each file has a low-level name that uniquely identifies itself, so it is called an inode number. And then when the file is stored in the storage device, then it uses the inode number to identify the file. So it's not a file name, okay? And the second important thing is about the dictionary, because dictionary in Linux is just a special type of file. So actually, like, if you create a dictionary in Linux, then that content will get a new inode to describe that directory. So each directory has an inode number as well. And here is a directory tree that you usually use in Linux. It always starts from the root. So here is a root, a backslash. And then it follows by several separators that, for example, if you are going to traverse from the root to the hide.txt, then the path will be backslash tmp10 and backslash hide.txt. Okay. And files referred by the absolute path name, it should be from root. So from root, this path is an absolute path. Okay, so because like there's no really difference between the dictionaries and files, so like the directories and files, so actually you can have the same name, because name is not really matters in Linux, because directories and files, even they have the same name, but they can have different inode number. So it is possible to do the things like this. Okay, so also like there is no Linux doesn't care about the file extension. So like .txt, even you remove the .txt, it still works. Okay. So I think here is the more important things about the file descriptor part. So file descriptor is an integer to identify the open file in all file-related operations. Okay. So it assigned by the kernel when a file is open and is valid only within a process. So different processes, they have their own file descriptor. Okay, so let's look at an example on the right-hand side. Okay, so this is process A and this is process B. So you can also see in process A and process B, they all have the process descriptor starts from 0, 1, and 2. And usually file descriptor or FD 0, 1, and 2, it usually means input file, output file, and error file. So usually the first three file descriptors, they usually are saying about the same things. And after file FD2, like FD3 to maybe thousands of file descriptors, it depends. For example, process A, if it opens a file, then it can get a file descriptor. Okay. Okay. So usually two processes may use the same file descriptor, but it doesn't mean they are using the same file. You can think about like different process, they have their own process descriptor. So even they have the same number, it doesn't mean like things. Okay. So inode, each file has just one inode. So noting like file descriptor is the concept for the process. Okay. A process open a file, they get a file descriptor. But inode is not the same thing. Inode is for the file that really stored in the storage device. So even there is no process, open a file, there's still inode number, there's still file in your storage device, right? So inode number is still there. Okay. So inode number is not only a number, because it also contains several metadata. For example, the access right, the date, the pointers to the file data, all these kind of things. Okay. Okay, so last time we said like actually there are several data structures here. There are process descriptor, there are file descriptors, there are inode table, and between them there are also open file table. So actually there is a question is about why we need all these three kind of like data structures here. Why not just merge them to one? Actually, it is possible to do it to merge them to one, but it will make the management become so complex. So here are some examples here. Okay, so the design of open file table is to relax the complexity of inode table and file descriptor table. Okay, so one more time, actually, it is possible to say like, let's split the rules of the open file tables into two parts. We can merge the first part related to the file descriptor to the file descriptor table, and the second part related to the inode table to the inode table. It is also possible, but here are several issues that we need to face. First, if process A and process B open the same file, in this example, FD0 in A, FD3 in B, for example, actually, FD0 here, and then FD3 is here, and you can see even these two, they point to different open file in the open file table, but actually they are opening the same things because they are from different process, so they get the different open file table entries. But both of these file descriptor, they point to the same inode 1976. Okay, so here are the issue is like, actually, for process A and process B, they own two different kind of file descriptor. That means like they have individual access mode and individual file offset. So what do I mean for individual access mode and individual file offset? Come to think about it, if one process opens a file with the read only and the other opens a file with write only, actually for inode, it doesn't really matter. I mean, for inode, it doesn't really know how many files are opening this file and in what kind of access right. So if we are going to move this management into the inode table, it will be super complex. Okay, so to make it simple, inode table only manage the like file on the storage, the things related to the data on the storage. So for this kind of processing information like access mode and file offset, actually they try to move them to another data structure called open file table. Okay, so let's go a little bit deeper. Like, for example, there is things called file offset, because if there are two processes or even there is the same process, they open the same files. And actually, for example, for the first process, maybe it is going to access the beginning of this file. But for the second process, it is going to access the tail of the file. Then actually, for the file, there is only have one file offset if they are pointed to the same open file table. Okay, so the thing is like this. If we only have the inode table, we don't have the open file table here. Then we have two processes. They are going to access the head and the tail of the file. Then inode table cannot handle it, because usually for inode table, we can only store one offset. Just like we can only store the only position like the file is now accessing now. But if with open file table, we can realize this design. In this example, like FD0 and FD3, they are pointed to different entries in the open file table. So they can maintain their own file offset. So when process A is accessing FD0, the file system knows like, hey, actually, FD0 is now accessing maybe the head of the file. And the other one would be this one. When process B's FD3 is accessing the tail of this file, then when the operating system schedule for the process B for FD3, then once again, we can move the offset to the tail of this file. So with this information, even there are multiple processes that are sharing the same files, we can still manage the process level issue. Okay, and because there are several processes, they can share the same file, so there is a reference count to count about like how many files are now sharing this inode. Okay, so there's another thing is about the locking, because I saw there are several questions that are talking about the locking, about like when there is two files, they open the same, two processes open the same file, and process A and process B, they are going to write different data into the same file. Then there is a rest condition if we don't use locking, right? So usually there is a file lock, and there are a lot of ways to implement a lock. But the key idea is like this. Actually, the lock is not stored in the open file table or inode. So the lock system in Linux, there's another system subsystem called lock systems. So when two processes, they are going to access the same file in the right operations, then, for example, process A, they're having like FD0, and FD0 needs to need to acquire the log from the log systems to write the data. So at the same time, actually, even process B's FD3, it is going to access the same, like I know, for example, it cannot do it because the file, the log now is not given to the FD0. So using this file descriptor table, a good way is about like in Linux, like the log is acquired in a granularity of file descriptor. So different process, even you are in the same process, you have different file descriptor, you still need to get the log before you are going to write the data to the file to avoid this kind of race condition issue. Okay. So there is another example is about the inheritance, because we say in Linux, like when process A forks process B, then process B shares most of the information of process A, including the file. So in this example, process A forks process B, for example, it will be look like this. The FD2, if you already in the process A, FD2 of both process A and process B, actually they pointed to the same open file table. So the reason is like the process A forks process B. So when the time the fork is finished, then process B FD2 is also pointing to the same entry in the open file table. So the same thing is like if like file B now, it needs to open the new one, or like it needs to do some update to this entry, then it will follow the copy on write issue. But if, sorry, the copy on write way. But if process B only reads the information, then it can just purely share with process A. Okay, so this is the way like how forking this kind of inheritance influence these structures. Okay, so that is for the file descriptor part. So let's move a little bit deep to the storage device. Okay, on the storage device, like we store the inode, and in addition to inode, we also store some other kind of informations here. So this is the directory tree. Here is a subdirectory from root, and then in the same label there are subdirectory 1 and then the file 0, and then inside the subdirectory 0 there are also file 1 and file 2. So these directory trees looks complex, right? So in the storage device, how to reflect this kind of directory? And here's an example. Actually, the boot and super block, I think it is not very critical here, because boot and super block, usually they are going to describe, for example, which device we are going to use to boot the systems. Okay, so the boot block you usually will be usually put in the device that we're going to boot. Usually is in maybe your SSD or hard disk drive. Okay, and the second one is super block. So super block is for each file system that has their own super block. So for example, if you have a disk and you are going to partition a disk into 2 partitions, but you're using different file systems, then on this device, you will have 2 super blocks. So 1 file system, 1 super block. So yeah. And then later on, there's inode tables. So inode table is going to maintain the information about the file, so including where the file is. So with this inode table, we can find where is the data block. Okay, for example, where is the file for file 1 in the storage device? Then we use the inode table to point to the address or location on the disk, so we can find, oh, actually it is on this locations. Okay, so I think the file part is quite intuitive, because file is just like a data, so you put the file there, so it doesn't have too many kind of things to talk about. But directory is quite spatial, goes like this. Okay, so each directory, actually you can see like it is a directory block. So directory block is just like a data block, but the difference is about in this kind of data block they put in the directory entries inside. So we call them the derivative block. But actually, the things is very similar to the data block. I would say like it is the same things, but the difference is about the content inside the data block is different. So for derivative block, actually, we only put the derivative entries inside, and the derivative entries will look like this. So like this, this is the name of file one, and then inode board is related to the file one. So using these derivative entries, it is possible to know like, hey, which file name can be linked with which inode. And using these entries, you can get the inode table in some places, and then you can get the content. Okay, so these derivative entries, that, for example, for here, for subdirectory 0, because inside this directory, there are 2 files here. So we will have 2 entries here. But come to think about, if you have another entries is one folder, then you will see the same things, like the folder name and the inode number for that folders. Okay, so this is how directory entries work like. Okay, so using these directory entries, actually you can do a recursive loop to get the whole directory tree. For example, if you start from the root, and you can go to find the child directory from the root, and then the child directory from the child directory. So you can go deeper and then to find out all the data in these file systems. Okay, so it all start from the root directory and checking the directory entries one by one. Okay, so this is a quick overview for the file system part. Actually, today we'll go deeper into about like, this is about the storage device. But when the CPU is going to access this information, actually, we'll move some of the information into the memory before we can access them. But what is the difference between the data in the memory and the different in the storage device? So, okay. So before that, let's give you a quick example. Last time, I think we start at the middle of the log structure file system. So I'll quickly go through the log structure file system. Okay, so the log structure file system, actually, it is designed to deal with the sequential access things. Because when we are going to write data in a sequential order, actually, it is not enough for hard disk drive, because hard disk drive usually it rotates all the time. So even we can write in a sequential way, but we cannot make sure how many processes are there writing the disk. Okay, so if there are multiple processes they are writing in the same sequential order, we still cannot make sure the data from the same process they are writing into the disk in the order they are predicted. So usually we need to issue a large number of contiguous write. So we need to group them together. So there is a concept, it's called write buffer, and write buffer is quite general usually. So we buffer all the objects in an in-memory segment and write a bunch of data to disk in a batch. So in this way, like this. Okay, so this is called a segment. So there are several data blocks, and then we have an inode to describe those data block, right? Because we need the inode to know where the block is. So if the data structure and the data is looking like this kind of format, and then we just group them in the write buffer, and then we will write into the hard disk drive in the same time, at the same times. So this is what we call a contiguous write. So if we are going to just write in a sequential order, you can think about like, we will first write DJ0, and then we will write DJ1 and DJ2 and DJ3, and then inode J. Okay, but the thing is about if we write it one by one, but for example, if we first write DJ0 and then we stop for like 5 minutes and we write another called DJ1, then for this 5 minutes, actually hard disk drive already rotates to several kind of circles there. So it is hard to know if DJ1 can really place in the nearby of the DJ0. Okay, but if we group them together and then we run them in a batch at the same times, then we will force this information can be written in the hard disk drive in the sequential way. Okay, so this is the slight difference between the sequential write and then contiguous write. Okay, so because we can, with using the buffer and we contiguously write the data on the hard disk drive. In this way, actually, when we are going to access the data, for example, if we are going to access data J, DJ, then we'll first check the inode. And with this inode number, with this inode information, we can know where is the block address. So this is block address 0, 1, 2, 3. So it has, okay, it has like A0 to A4, A3, then we can get the data out. Okay, so the good thing is about if we read out this data continuously, because the physical limitation of the hard disk drive, it always rotate in the same directions. So those data can be read out at the same time. And in the memory, CPU will process the data. So CPU will know, oh, okay, so I know J here includes several data blocks, and we luckily already read them into the memory, so we don't need the second access here. Okay, so this is the concept about why we need this kind of log structure file system. Okay, but here's the question is, but how to find an inode in a disk? Because you can see now inode actually they separate across the hard disk drive, right? And we say if we can find an inode, then we can find the data. But how to find an inode? So this time we say like, actually in the old Unix file systems, they are putting in the fixed locations. So when at the beginning, like we are going to partition the disk and then we are going to mount the file system on it, actually we will allocate a continuous space here and a space like A start here, and then before the A start, actually there are all for inode. So we put the inodes together at the bottom of the disk, or maybe at the head of the disk. So in this way, we can easily find where is the inode, right? Because if we only need to store the A start. With this A start, then plotting the offset of the inode size, actually we can know which inode it is. Okay, so in this way, in this old Unix file system way, we can easily get the data and inode. But the thing is about, that means like for every access, we need to access two locations on the disk. One is about the inode location, another is about data location. So the access latency will be twice for getting one data. Okay. Okay, so a better way is about why not just move the inode and data together? Because inode 1 is for data 1, inode 2 is for data 2. We already know these things. So if we can put inode J with DJ and inode K with DK, actually luckily if we access the inode J, then actually the head of the disk can also read out the following data. It doesn't really need to jump to other locations. So in this way, the performance can be like only need half of the time we can get the data out. Okay. However, inodes now are scattered, so we cannot get an inode. So now we use another new data structure called inode map. So inode map, actually you can think about like, this is a summary of several inodes. So like this, inode 0 to J means like we are going to summarize the information of inode 0 to inode J, those J plus 1 information here. So for example, inode 0, inode 1, inode J, they are placing like AX, AY, and A4, those locations. So with reading inode map, we can actually get where the inode is. Okay. So using the inode map, we can get inode, and using the inode, we can get the data out. Okay, but the same question is about like, with using the inode map, yes, we can quickly identify a batch of the inodes, but how about inode map? So we still need a non-fixed location to know the inode map. So in the log sorted file system, we will use this checkpoint region we put at the very beginning of the hard disk drive. So this checkpoint region, you can think about is another summarize of the inode map. Okay, so for this summarize, actually for inode map 0 to J, it will point to imap 0 to J, and it starts from A5. Okay, so with this, we can make the checkpoint region super small, because the checkpoint region as the data for summarize the inode map. And inode map is a summarize for inode. Okay. So this is how the log chart file system used to get the data. First of all, you need to get the checkpoint region. And usually, because the checkpoint region is super small, so checkpoint region usually they would be put into the memory. So actually, we only need to care about where is the inode map and where is the inode. So actually, we can get a faster access time compared with the old Unix file systems. Okay. Okay. So there is an example to let you know about what about the directories. So I think from now here there will be a new stuff that were not included last week, the past 2 weeks, I think. So we have inode map, inode directory, inode directory here. Okay. So like this, a directory is just a collection of name, inode number, and mappings. So a directory like a file has their own inode. So there are the things you already know. So in this example, if inside the inode map, there are 2 different kind of inode. One is for directory and one is for the data itself. So with parsing inode map, actually we can know actually the first directory we can get from A3 here. So this is for the directory. So it should be /home. And for A1 here is for the test, the data about the test. So it is on A1. Okay. So with using inode map, we can look at 2 different kind of inodes. And one is for directory and one is for the file. So for the directory inode, actually we can get the data according to the inode number from here. And then for getting the directory data, actually we can use the directory inode to get it. And for getting the data, we can use the data inode to get the data. Okay, so like this. Okay, but here comes an issue. If we are going to update test, or if we are going to update the data, so data here is DJ. So after updating the data, actually we need to move to like DJ here, a new data here. Okay. And because the data is moved to the new DJ, the reason like DJ needs to place it in another direction, another position is because maybe after accessing DJ, DJ becomes larger. So when DJ becomes larger here, we cannot directly in place update the data here. Okay, so if DJ becomes larger, then we need to find another place to put it. Okay, so you can think about we will, according to the log structure file system, we'll put into the tail of this hard disk drive. So maybe it's here, DJ. And because the location of DJ is updated, so the corresponding inode should also be updated, right? Because inside the inode, there will maintain the block address information. So now the DJ is moved to A5, then inode J here will update the block address to A5. Okay, and because the inode J is updated, so the inode map should also be updated, right? Because inode map inside it is now pointed to say like, hey, actually, data J is now at the inode of data J is now at A1, but actually it is now updated to A6. So IMAP will be updated again to point it to the A6 for inode J. Okay. Okay, but what will happen if there is no inode map? Okay, it will be like this. Because we say, hey, actually we have inode directory and inode J here. Okay, and they're all the same things. Inode directory will point to the directory data, and inode J will point to the data itself. So, okay. So if we do the same thing, we update the data, update the text. So data is called DJ. So after update, we will put the DJ at the tail. There are same things for the upper. So then after that, we need to update the inode J. Okay, but the thing is about actually, if we update inode J here, then the directory entry should also be updated, because the directory entry will point it to the inode data for itself, because test is under directory entries here. So when test is updated to other place, then the directory should be also updated. Okay, so like this, we need to also update the D directory to a new place to say like, hey, actually test.j, or sorry, the data test is already moved to the new place. Okay. And the same thing is because we update the directory, so the inode directory should also be updated. Okay. So if there's no inode map to help to summarize the inode informations, if only there's inode, then when we update the data in some place, then we need to also update all the parent directory from this path. So there will be a recursive update here. Okay. So the recursive update problems will affect the parents, and then you will cause a performance issue here. So inode map, not only like using the inode map, we can also rely on the checkpoint region. So the checkpoint region can put into the memory for the fast checking. This is one of the advantage. The other advantage is with using this inode map, actually we can avoid this kind of recursive update problem for updating the directory. For updating the data if it is on a deep directory. Okay, so this is some kind of things to let you know for a low structure file system stuff. Okay. Okay, so I think file system will stop here because actually different file system, they have different designs. So it is hard to go into detail for each of the file systems. And low structure file system is the very basic file systems. I think you can think about like this. Most of the well-known file system now, they will adopt some of the concepts from the low structure file system. Okay, but because like there are a lot of different file systems in our like no matter Linux or Windows, actually you can choose about you're going to use the NTFS or like you are going to use for the ext4 or like exFAT. So there are a lot of options there. So it is hard for the programmers to like send different kind of requests for different file system, right? I mean, if you are a programmer, then if in your systems there are 10 file systems, so you need to write your code in 10 different ways. Just want to communicate with this file system. So it is also like it is inefficient, but it is still possible. So actually, virtual file system is coming to solve this problem. Is it possible to virtualize the functions for most of the file system? For example, actually, for different file system, usually they have the read operation, they have the write operation, they have delete, they have the directory create. We can also remove the directory. So those of the general function, actually, they share across the file systems. So if we can abstract those kind of functions by a thing called virtual file system, then we only need one code to manage all these kind of file system. I mean, virtual file system will help you to take care. For example, if one user now is going to interact with the virtual file systems, then if the virtual file system know actually this user A is going to access like ext4, then virtual file system will help to translate the code for compatible with the ext4. So virtual file system can help you to manage this kind of complexity to make the programmers don't really need to deal with different kind of file systems. Okay, so like the goal for the virtual file system is to enable programs to use standard Unix system code to work regardless of the file system or underlying physical medium. So you can think about, for most of the programmers, they will think, actually, no matter they are using NTFS, ext4, exFAT, or like those kind of stuff, actually they looks very similar, or even there's no difference between them. And this is because there is a virtual file system between the programmer and the file systems. If there is no virtual file system, then each programmer should handle different way. For example, maybe the parameters, for the read functions for different kind of file systems, maybe the parameters numbers will be different. For example, for ext4, maybe for ext4 you need like 4 parameters for the read, but maybe for like exFed, maybe you only need 3 parameters. So you need to rewrite your code to follow this different kind of file system. But now virtual file system help you to deal with this kind of stuff. Okay, so this is the reason why we're going to give you some brief, I would say like brief knowledge about the virtual file system. Okay, actually like with the virtual file system and block.io layer, there are all the abstraction layers. So abstractions layer is just the most objective for the abstractions layer is to let the programmers feel very simple to program, to control this kind of like device and file systems, because they don't really need to worry about, actually there are different kind of device, there are different kind of file system, they need to write different kind of code. They only need to use one, I would say like standard library. They can control all this kind of stuff. Okay. So the thing will be like this. Actually, for user space, most of the users, they only know read, write, like make directory, this kind of functions. But actually, system in the operating system, virtual file system will hook the right system code with the system write, this kind of virtual file system function. And for this virtual file system function, actually, this one will hook to all different kind of file systems. For example, for exFed, they have their own implementation for write method. And maybe for ext4, ext3, ext2, they all have different implementations for the write. And VFS will help to hook all this kind of file system together. Okay, so this is about the virtual file system. So actually, after you learn virtual file system, actually you will have a very, also like will have a very concrete concept about how file system is designed. Because virtual file system will include all of the key design for file system. Otherwise, it cannot really be simple to hook with all different kind of file systems. Okay. So because like virtual file system already be developed for like several decades here. So at the very first version of the virtual file system, it refers to the ext2 file systems. Okay, so ext2 is very classic and very old file systems. And the VFS as an abstract layer, I mean, the design of the VFS is referred to this ext2. And also most of the new file system, they also share very similar points with the ext2. I mean, there are differences, but because most of the concept, they are start from the ext2. Like ext3, ext family, they share the same concept for the ext2. And also like different exFed and NTFS, they also use similar idea from ext2. So actually, VFS, most of the data structures, most of the interface, they are from ext2. Okay. Okay. So actually, for VFS, here are some mapping between the data structure inside the memory and on the storage. And this is what I mentioned in the first few slides about, actually, in this slides, we only talk about what data look inside the storage device, right? But when the data is read into the memory, it will be a little bit different. Okay. So actually for VFS, there are 4 primary object types, or you can think about there are 4 very critical data structures here. So the first one is superblock object. So superblock object represents a specific mounted file systems. So as we mentioned before, for each file system, you get 1 superblock. So if on one disk, you have 10 file systems, then you need 10 superblocks on that disk. Okay. And the second one will be inode. So inode object is to represent a specific file on the storage device. Okay. And the third one will be the entries objects. So it represents a directory entry, which is a single component of the path. Okay. Oh, sorry. let me give you an example for D entries. So because if you have a path slash user slash home slash temp, and for this path, actually you will have 4 D entries. One is for temp, one is for home, one is for user, and one is for the root, because you have 4 layers. So the VFS will parse it and then break to 4 D entries objects. So for each of the component, it will get 1 D entry object. The entry object for the root, the entry object for the user, for the home, for the temp. And file object, actually, it is to represent an open file as associated with a process. So today we'll focus on the middle, inode and D entries. The reason is actually file is just about using the file descriptor and then to do some things. And the super block, actually, it is about when you mount the file system, and what information do you need? And the key thing is about, so how about how inode and D entries, they work together? Okay. Okay, so I think this one is super important. So let me rephrase again. The VFS treats directories as normal files. So there is not a specific directory object here because they are all managed by the inode. Okay, it is inode, not D entries. I'll talk about what is D entries about. But D entries is not purely for directory entry. D entries is usually for the fast lookup for looking up where is the data in what kind of directory. So it doesn't really mean this is directory entries. Okay. Okay. So after talking about the data structure, there's another important thing is about the things called operations. So operations is more like when we talk about objects, object is like a data structure, like the data structure for inode, the data structure for superblock, the data structure for D entries, right? But how about, for example, if we are going to create a new inode, if we are going to remove a directory, if we are going to use a hard link, if we are going to create a soft link, then how to implement this kind of algorithm? So they are all included in the operations. So operations you can think about is the algorithm that are going to do some things. Okay. Okay, so like this, there are a lot of operations. There are super operations, inode operation, the entries operation, file operations. So I think actually even that looks like a lot, and maybe there are a lot of noisy words here, but you can think about like this. Actually, they are talking about very similar concept. It's about we need some methods to manage file system. Then it is super operations. For example, if we are going to sync the file system, if you are going to create the file system, if you are going to destroy the file systems, then those methods, how to implement it, then it is about a super operation. And here is one interesting thing is actually using these operations. For example, if now we are going to deal with ext4 and xfs, because there are 2 different kind of file system here. So each file system will show their own operation implementation. For example, for ext4 and xfs, they both have remove directory, but maybe their logistic is quite different from each other. So the operations will help to point to the remove directory functions implemented by ext4 and xfs. So when you are using the ext4, then operations for remove directory will use a pointer to point to the code for ext4. And now if you are going to use the xfs, then the pointer will point it to the functions for xfs. So these operations, they are all defined by different file systems. Okay. So we'll give you more kind of examples later to tell you about, to give you more kind of feelings about what this kind of operations look like. Okay. So first of all, let's start from a very, I think, basic concept is about a superblock object. So superblock object is designed to store information describing the file system. So when mounted, a file system invokes allocate-super. So this will raise a superblock of the disk and fills it in the superblock object. Okay, so usually when we are talking about blah 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 object, VFS object, superblock object, dn-trees object, those kind of objects, they are all the data structure inside the memory. Okay, not on the storage. They're all about the memory data structures here. Okay, because you see here, like read is superblock of the disk. So we already have a superblock on the disk, right? Because when at the very beginning, like you're going to partition the disk and you are going to mount a file system on the disk, and at that time you already put a superblock in the disk. Okay, but when you are going to use this file system, you need to read this kind of superblock data to the memory to then becomes a superblock superblock object. So the data structure in memory will look like this kind of stuff. Actually, there are a lot, but I'm just going to show you a very important thing is inside this object, inside this data structure, actually there is a pointer. This is super operations. So these operations will point to the operations that relate to the superblock like this. So this one, S- operation will point to all different operations or like functions supported by the superblock. So superblocks operation can get which specific operations according to the superblock, and then using this pointer, we can point into these operations. And then for each kind of the rotate inode, dirty inode, write inode, drop inode, this one can also be hooked by different file system. So each file system has their own write inode, like drop inode or data inode way. Then this hook can be hooked to different file system. Okay, because we are now using a virtual file system, so actually we need a real file system specific under this file system, under this virtual file system. And the implementation for this file system will be directly hooked with this virtual file system operation stuff. Okay, so I think let's take a 10 and then come back later.